The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next speaker is Armin Ziari. Armin is a design engineer at Can-Do Energy Inc. He recently joined that company in Toronto. Prior to that, he was a postdoctoral fellow at Ryerson University. And the title of Armin's presentation is Crack Control in Two-Way Reinforced Concrete Panels.
Hello, everyone. So this presentation is about the crack control in two-way reinforced concrete panels. This is a part of my PhD and postdoctoral project at Ryerson University with Dr. Kianush and our industry partner, Risto Pratik from Engineering Associate. And the project is also recently supported by Can-Do. So today I will explain the research significance and scope. Then I explain my proposed crack prediction model and experimental program and how we verified that, and the design guide, conclusions and acknowledgements. Why crack control is significant? Probably due to three main reasons of serviceability, durability, and appearance. Examples are deflection control, leakage control, permeability reduction, and corrosion reduction. There are some shortcomings in the current design codes. They don't consider any, they are just considering simple loading conditions like pure bending or pure tension. They don't have any reliable crack control for two-way members, and they ignore repeated loading effects or long-term effects. The big picture of the research was to experimentally investigate the cracking and leakage behavior of two-way panels. Then I will go and use a finite element technique to find different aspects of reinforced concrete cracking. And at the end, we were hoping to develop a new crack model for two-way panels. There are many examples of two-way elements like floor slabs or in liquid containing tanks or nuclear containments. They all work in two-way action. Just one example, this is a sidewall of a liquid containing tank, and you can see that is under two-way action because of the tension in horizontal and the bending in vertical. The crack pattern that you would expect is some form of this, orthogonal cracks and a combination of diagonal cracks. So obviously you cannot predict these cracks with usual one-way crack models. We propose a set of equations to predict the cracking load as stabilized cracking load, minimum crack spacing, maximum crack spacing, and maximum crack rate at stabilized cracking. These are all developed based on physics of cracking, and different parameters are involved in these equations that I purely try to find each parameter through finite element simulation. So obviously further improvement in each of these parameters can result in further improvement of the overall crack prediction. So I briefly try to explain the different parameters involved here and how I will get an estimation of each parameter. First thing is stabilized cracking definition. The stabilized cracking is at a load that beyond which increasing the load will not cause any additional cracking to form. So pretty much the strain stress in the concrete and the steel is established, and further increasing the load only increases the strain in the steel. So having an idea of this distribution is necessary to predict the crack. The first equation, stabilized cracking load. One parameter that's introduced here is splitting stresses. In a two-way element, because we have a web of orthogonal reinforcements, the transverse reinforcement can contribute to the stresses through splitting stresses. These are splitting stresses caused by radial stresses, bond radial stresses. So we have to have an idea of how much is this stress. For that, we need to look at the mechanism of bond. The bond is normally transferred from the steel to the concrete through diagonal force, so which has two components of tangential and radial. So this component radial can cause splitting stresses. So to simulate that in finite element, I used diagonal link elements at various angles of 30 to 45 degrees. Also, I used, well, actually, these are not coming, right? But I used another technique, which is bond layer. I reduced the tensile strength of concrete at the layer close to this reinforcing bar, so the forces would transfer from the steel to the concrete through diagonal compression stress rather than tension. So the idea is to increase the radial stresses to get closer to what is actually happening in the actual structure. The model is compared with two experiments, one from CanCom, and we found that bond layer is giving good results for tangential shear stresses, and the perfect bond, which is normally used by others, is far from the actual case. Also, another test, I compared it with another test, and we found that the bond layer is giving good results. So, with the verified finite element model, again comparing the bond layer model, you see that the bond layer is giving higher radial stress. These are radial stresses. So if you use just perfect bond, which is sharing the node between the steel and concrete, just simply sharing the node, then you will underestimate these radial stresses. Bond layer is closer to the actual. So with that finite element technique, I did some parametric study to find the splitting stresses, which are concentrated at 1/3. I don't know why everything is just messed up here, but the stresses are concentrated at 1/3 at loading end of this member. So with the parametric study, you can have some idea from this chart of how much is your splitting stress. This is average splitting stress versus steel stress versus concrete. This one, the concrete cover to bar diameter ratio. So from this graph, you can have some idea of how much is this stress. The next thing is shrinkage stress. Obviously, when concrete will shrink, want to shrink, this rebar does not allow the concrete to shrink, so stresses, tensile stresses will develop in the concrete, and again, finite elements give us an idea of how much is this stresses to be used in this equation. The effective tension area are also important. The effective tension area is the depth of this area that is affected by the reinforcement. This depth is also introduced through another equation with a new factor of k prime tx. And to find that k prime, we do parametric study on flexural beams, and this darker area means this area of concrete is affected by the reinforcement, and the depth of that, which is interested, can be found from the graph from parametric study. For the minimum crack spacing, all the parameters are almost the same as the other equation, only the shear bond stress. Bond shear stress is new in this equation. Again, that can be also found from parametric study on just tie member, and you can have an idea of how much is the peak bond shear stress for different concrete. This one is concrete cover to bar diameter ratio, and actually this one is concrete cover to bar diameter ratio, and this is a student stress. So at each different situations, you can find the peak bond stress from this graph. For the maximum crack spacing, a new theory is proposed. If we have a setup of the crack arrangement like this picture, then no additional crack can form between these two cracks, because the stress just comes short of the tensile strength of concrete. But we believe that this arrangement is very low, has a very low probability, and a more higher probability is for one of these cracks happening at least one of them happening at the location of transverse reinforcement. So in that case, the equation would be the second one. For the crack width equation, we introduced a new factor. All the factors are quite obvious, but the new factor that is presented in this one is alpha SP, which is a reduction factor for splitting. I explained that why we have such a factor in two-way panels. This experiment that we did, I will explain that in a bit, but just to explain that factor, you see that in a two-way element, when orthogonal cracks happen, if the orthogonal crack just go along one of these reinforcements, you see that F3 just coincide with this crack, and the strain reading for this F3 reinforcement is much higher than other two reinforcements like F4 and F5. So for crack width prediction, we have to consider that in two-way panels, because the orthogonal crackings can damage the bond. Just showing that with the parametric study, finite element parametric study, we can see that we have almost 55% reduction in the bond stress due to splitting cracks or longitudinal cracks along the reinforcing bars that can happen in two-way panels. So we introduce that into our equation as well. We did an experiment to verify our equation, and this experiment is done in Ryerson. We put reinforced concrete panels in tension in one direction and bending moment in the other direction. This is showing the schematic of the setup, which on one side the reinforcements are fixed to the strong wall, and the other side is pushed against the strong wall through two jacks on the side. So this is another view on the side view. You can see everything is free to slip, and one side is fixed to the strong wall, the other side is pushed. So in this direction we have tension. In the other direction we have bending because of this center jack pushing upward, and the two ends of the panel is fixed to the floor. This is showing an image of the test setup. Comparing the results for this experiment with another model from CEB FIP model code 90. We can see that the error is for one-way. This is a one-way crack model. And for cracking loads, we have error from 45 to 79% for direct tension and 50 to 82% for flexural cracks. However, the proposed model has much lower errors, range of 5 to 19. Also, the crack spacing is compared with model code 90, Eurocode 2, and some equation from RISC from another researcher. And we found better results from the proposed model than any of these equations. Also, for crack width comparison with the experiment, we see that most of one-way cracking models are underestimating the flexural cracks in the right column. There is one model from Navy which is in two-way flexure, and that's really overestimating the crack width for the case that we tested. Also for direct tension, the Eurocode is really giving wrong results, and MC90 is, again, the trend is different. But in all cases, the proposed model is acceptable. So that brings me to the main issue, which is a design guide in ACI 350. I did parametric study with the equation that I proposed to limit the crack width at 0.23, which is similar to what we have in ACI 350. For different spacing of reinforcements, I have to limit the stress in the steel. For direct tension and for flexure, we have two graphs. Comparing these results for flexural cracks, because ACI 350 only have recommendations for flexural cracks and not direct tension cracks. So for flexural cracks, you see that how much they're off from each other. You see, this is recommended by ACI 350 is really underestimating the crack width. For instance, for this crack width, if we use 150 millimeter spacing for reinforcing bars, we have to limit the stress at 100, while ACI allows it to go up to 175, which is more than what should be. So with this equation, this is just one example of the design guide that I could produce, but these can be reproduced for all different cases with these equations. So my conclusions are a new crack prediction model for two-way reinforced concrete panels, in which I use finite element parametric study to find different parameters like bond, average splitting, stress, and new factor for effective tension area, shrinkage-induced tensile stresses, bond strength reduction due to splitting cracks. We have a better argument with this model, and also we can provide new accurate design guidelines to replace unconservative ACI design guidelines. I want to acknowledge the financial support from NSERC, Ryerson University, and CANDU. Thank you.
When you were doing your experiments, what tool did you actually use to measure the crack width?
There was
How many issues per crack?
there were two type of gauges, crack gauges. We normally use eight gauges, 3 gauge for with one type, which I don't remember the name, and there is 5 another type. It was pi gauge. Yeah, the pi gauge was not as accurate as the other one, but the other one was, we had only 3 of them, but in total we had eight gauges.
I mean, you had a slide showing the ACI 350 versus some other, the previous one. Yeah. Can you just describe one of these that you have ACI 350 shown as vertical line? What do these represent?
So this is for flexural cracks. So ACI means this crack. For instance, for this one, this is ACI 350. So it means the load at this stage is where the ACI recommending to limit your stresses, and that goes up to almost 0.4 millimeter crack from the experiment. If you see that as 0.4, which is not the same as what they're looking.
For two-way flexure.
This is for two-way, yeah.
Two-way flexure.
Yeah, for two-way. So their actual crack rate that they're limiting is 0.4. I don't know if they intended to limit it to 0.4. I think their intention was to limit it to 0.27.
Almost 0.01 inches. So that this is close to 0.02. Right?
So definitely they're not in agreement with the experiment.
On that chart, it looks like some of them get down there around that 0.1 square inches. Which methods that have been used historically did a better job getting it down to where we're looking at?
I would say, because it's not clear there, I think Frush, for flexure cracks, I would say Frush is doing better. Yeah, ACI is not that far from the actual case for flexure cracks compared to other models. For dye tension cracks, we don't have anything from ACI. Only model code 90 or Eurocode, but both of them are very off from the actual case. But for flexure, I would say still Frush model and ACI are giving a little bit better results than other models. But it's still, I think from the next slide, you can see that they're still off for two-way. Yeah.